3I Atlas maintains its trajectory despite the powerful solar flares, with new updates coming in. This marks one of the most intense moments in the astronomical monitoring of this year. Not because 3I Atlas has changed course, but precisely because it has not done so, even after the Sun unleashed some of the most energetic explosions of its current cycle. In recent weeks, the instruments observing solar activity recorded events that typically affect everything from artificial satellites to the dynamics of the solar wind. But this time there was additional interest, an interstellar object crossing through the solar system. Right during the peak of these emissions, from the very first minutes of the explosion, the observatories knew that any slight alteration in the flow of solar particles could generate a minor deviation in the object's path, enough for its orbit to require recalibration with extreme precision. However, as the data was analyzed in real time, something began to catch the attention of the scientific teams. Despite the magnitude of the explosions, the trajectory of 3I Atlas remained exactly where it was supposed to be, without measurable variations within the margins of error. This immediate stability sparked a new wave of interest because it confirmed not only its extremely high speed and considerable mass, but also the way it interacts with the extreme conditions around the Sun. With each update, the feeling of witnessing a truly resilient object became clearer, and yet the monitoring intensified because in astronomy nothing is certain until the data has been fully reviewed, compared, and validated by multiple observatories. Welcome to this updated analysis on one of the most studied objects of the year. Before we continue with the video, there are 3 things you need to do right now. First, like this content so that these verified updates reach more observers around the world. Second, subscribe and turn on all notifications so you don't miss a single real-time update on its unchanged trajectory. And third, go down to the comments section right now and write the word resilient to add your name to the international registry of those witnessing this unprecedented demonstration of orbital stability. Do it now. At this moment, 3I Atlas continues its journey through the solar system while the most important observatories monitor every detail of its passage. The recent solar activity generated enormous interest because it coincided with a key stage of its approach. When the Sun releases such energetic explosions, the dynamics of the solar wind can temporarily modify the behavior of particles, plasma, and magnetic fields around small objects traveling at high speed. That is why it was essential to know whether 3I Atlas would maintain its orbital stability or whether it would show a slight variation that would force a recalculation of its trajectory. The surprising thing is that even under such extreme solar conditions, the object's orbit remained identical within the expected values. This not only reaffirms the precision with which its movement has been tracked, but also the ability of modern instruments to detect any minimal oscillation. Throughout this content, what was known before the explosions will be reviewed, what happened during the peak of activity, and what the subsequent data reveal about the orbital resilience of this interstellar visitor. All the information presented here is based exclusively on observational data, instrumental comparisons, and confirmed scientific analyses. Since 3I Atlas was first identified, the scientific community understood that it was not an ordinary object. Its speed, its hyperbolic trajectory, and the way it appeared crossing the sky during a period of intense observational activity immediately sparked interest because every interstellar object that enters the solar system represents a unique opportunity to study material that comes from regions completely outside the Sun's influence, unlike the bodies that belong to our own planetary family, whose origin and composition are better understood thanks to centuries of tracking. An interstellar object carries with it a physical history that was not formed under the same conditions. That difference turns every measurement, image, spectrum, and record into data of enormous value, because they allow comparisons of what processes are universal and which are exclusive to our cosmic neighborhood. In the case of 3I Atlas, the first stage of analysis focused on confirming its interstellar nature through extremely precise orbital calculations, as the accumulated measurements showed that its eccentricity clearly exceeded the value necessary for classification. As an interstellar visitor, the research teams expanded monitoring to observe changes in brightness, variations in the coma, material emissions, and any signal that might indicate distinct dynamic behavior. The instruments of the Atlas system that made the initial detection were quickly supported by telescopes installed at different latitudes, which allowed for a wide observation window. Cooperation was essential because every minute counted. The community knew that the deeper 3I Atlas entered the inner region of the solar system, the more physical influences it would face, and each one could affect aspects such as its brightness or surface activity. As the first weeks of observation progressed, the trajectory of 3I Atlas was defined with remarkable precision. The calculations showed that its passage would be fast, defined, and without significant gravitational captures within the planetary environment. Even so, the measurements required continuous adjustments, because any small error in the observed position could generate a considerable change in the orbital projection. That is why astronomers compared data from optical telescopes with infrared records and orbital prediction models calibrated day by day. The most interesting aspect is that even in this initial phase, the need to monitor the object during important solar events was already perceived, because it coincided with a period in which the Sun was showing signs of intensification in its activity cycle. Although that detail did not generate alarm, it did create scientific expectation, since relatively small objects, such as some comets or minor asteroids, can experience slight effects derived from the solar wind, especially when passing through regions dominated by energetic particles and rapidly varying magnetic fields. 3I Atlas was moving toward more illuminated regions. The instruments detected a gradual increase in its brightness, something expected for bodies with surface activity, since proximity to the Sun increases the release of volatile material. However, although this behavior sparked technical discussions, it was not interpreted as a sign of instability, but as a natural part of the heating process. Even so, there was additional interest in knowing how the object would react to a solar environment that was about to experience a series of significant explosions. Astronomers knew that the solar wind resulting from these events can temporarily alter the conditions around small bodies, although it does not necessarily modify their trajectory. To confirm any possibility, it was necessary to compare previous data, record behavior during the event, and review possible variations afterward. The phase prior to the solar explosions was crucial because it allowed for the establishment of a very precise baseline. The positions recorded by ground-based and space-based telescopes offered a series of coordinates detailed enough to detect any alteration, even if it was extremely small. That database would later serve to rigorously evaluate scientifically whether 3I Atlas had experienced any deviation. Furthermore, it was during this period that the Rubin Observatory began to record ideal conditions for obtaining deep images, which allowed the trajectory to be fixed even better. The brightness behavior was also measured by infrared instruments that compared the apparent surface temperature with the values expected for an object of this type approaching the Sun. All these measurements became fundamental pieces for the stage that was to come. The importance of this initial phase cannot be underestimated because all subsequent information depends directly on the quality of the previous data. When the Sun began its sequence of explosions, the teams were already prepared with an extremely refined orbital map. This means that any minimal variation caused by solar activity would be detected immediately. Up to that point, 3I Atlas demonstrated stable and predictable behavior, but no one could anticipate whether the explosions would modify the interaction conditions between the object and the energetic particle environment. That is why this pre-observation stage marked the starting point, indispensable for comparing what would come later, and it also reinforced the importance of each accumulated measurement before solar activity reached its peak. When the first signs began to be recorded that the Sun would enter a period of intense activity, the observatories already had it clear that constant vigilance was necessary both over the solar surface and over the bodies transiting the inner region of the solar system. Solar explosions, also known as flares, represent sudden releases of energy in the solar atmosphere that can generate electrical, electromagnetic, and energetic impacts at great distances. Although these events are not rare during the maximum of a solar cycle, the temporal coincidence with the presence of 3I Atlas created additional interest because the instruments had the opportunity to observe simultaneously a high-intensity solar phenomenon and an interstellar object crossing a zone influenced by energetic particles. This combination did not occur frequently, and that is why the teams began to prepare models and simulations to anticipate what type of data might emerge from this convergence. As the flares increased in frequency and intensity, the satellites dedicated to monitoring solar activity confirmed that the events were reaching particularly high levels within the cycle. Observatories such as the Solar Dynamics Observatory, the Solar and Heliospheric Observatory, and the Parker Solar Probe mission sent real-time updates showing the release of plasma, shock waves, and high-energy particles moving toward interplanetary space. These measurements helped define the size of each event and its possible impact on the heliosphere. In parallel, the telescopes tracking the trajectory of 3I Atlas coordinated to record its position more frequently than usual, because any small variation detected at that moment would be key to understanding how solar activity would influence, if it influenced at all, a body of interstellar origin. Intense solar activity does not affect all objects in the same way. It depends on their mass, composition, surface, distance from the Sun, and physical structure. For objects with active nuclei, such as some comets, energetic particles can temporarily elevate surface activity, causing visible changes in brightness from great distances. However, the direct impact on the trajectory is usually minimal, especially in bodies with significant mass and high speed like 3I Atlas. Even so, scientists wanted to confirm this with real data and not just models. During this period, the records showed a sun releasing energy through flares that reached the upper regions of the solar corona, generating coronal mass ejections that expanded rapidly towards space. These ejections, known as coronal mass ejections, can temporarily modify the density of the solar wind, and therefore it was fundamental to evaluate whether these variations would have any perceptible effect on the interstellar visitor. While solar instruments captured every detail of the phenomenon, ground-based observatories continued to obtain optical measurements of the exact position of 3I Atlas. The coordination between both types of measurements created a very valuable scientific panorama because it allowed the synchronization of solar activity peaks with the specific moments when the object was recorded in the sky. By comparing the data, the teams could evaluate whether any change in the pressure exerted by the solar wind coincided with a detectable alteration in the object's trajectory. The first results showed that the position remained stable, but scientists knew that conclusions could not be rushed. Often, analysis requires accumulating several hours or days of data before something can be stated with absolute precision. Each solar explosion released a quantity of particles that was measured through instruments on board specialized satellites. And all these measurements were correlated with the displacement of 3I Atlas through the previously established coordinates. The intensity of the solar phenomenon was such that even some artificial satellites near Earth experienced slight electrical disturbances. These alterations demonstrated the magnitude of the solar activity and reinforced the importance of continuing to measure the behavior of the interstellar visitor. Despite these local disturbances, the astronomical data showed a firm trajectory, without appreciable deviations, which began to attract the attention of analysts. The stability of 3I Atlas during these extreme conditions revealed notable physical characteristics and allowed the inference that the pressure exerted by the solar wind had a limited effect on its orbital displacement. Even so, vigilance did not decrease. On the contrary, it increased. The observatories knew that some coronal mass ejections can take time to reach different regions of the solar system due to the variable speed of the particles. This meant that even hours or days after the explosions, the conditions around it could change. Scientific expectation remained high while the data continued to flow. The importance of this observation process lay not only in determining whether the trajectory was altered, but also in understanding how an interstellar object reacts to intense solar conditions. The interaction between radiation, plasma, and icy bodies from other stellar systems is a relatively new field of research with few available examples. Each real-time measurement generated additional knowledge about the physical properties of the object and about how bodies from entirely different environments behave. During the strongest peaks of the solar phenomenon, some instruments detected slight increases in the object's brightness, something that had already been observed on other occasions and that was not considered out of the ordinary. The teams compared these records with previous values to confirm whether the change was a consequence of natural heating due to solar approach or whether it had a direct relationship with the energetic particles released by the flares. The analysis indicated that the brightness pattern remained consistent with normal behavior, without unexpected irregularities. This stability reinforced the idea that the object responded to the solar environment in a predictable way and that the explosions, although intense, did not have the necessary capacity to modify its route. At the end of the period of the most intense explosions, observers already had a considerable set of data showing stable behavior, both in brightness and position. Although further comparisons were still pending, this stage already offered one of the most relevant conclusions of the 3I Atlas study. It was resisting extreme solar conditions without showing signs of orbital deviation. This result strengthened the scientific importance of the object and opened new questions about its composition, density, and internal structure, since its stability could reflect physical characteristics of great relevance for the study of bodies coming from outside the solar system. While the solar explosions reached extraordinary levels, an inevitable question arose among specialists. To what extent can solar activity really influence the movement of a body traveling through the solar system? To answer that rigorously, it was necessary to first analyze the physical interactions known between solar radiation, the solar wind, and small bodies crossing this region. Although it might seem intuitive to think that an explosion of such magnitude could alter an object's trajectory, scientific reality shows that these interactions are much more complex and depend on a series of factors that cannot be generalized. This explains why the scientific community followed every detail with such attention when 3I Atlas approached the environment affected by the increase in energetic particles. The solar wind, composed mainly of protons, electrons, and highly energetic particles, travels at speeds that vary according to the state of solar activity. During flares and coronal mass ejections, the density and speed of these particles temporarily increase, creating additional pressure on any object in their path. This pressure is known as radiation pressure or solar wind pressure. In extremely small bodies such as microscopic dust or tiny fragments, this pressure can generate perceptible movements, causing those particles to change direction or even be completely expelled to other regions. However, when it comes to objects with significant mass such as comets, asteroids, or compact core interstellar visitors, the effect is usually practically imperceptible. This happens because the amount of energy needed to alter the trajectory of a macroscopic body is immensely greater than that exerted by the solar wind, even in its most intense phases. With 3I Atlas, the situation was even clearer from a physical point of view. The object travels at extremely high speeds, far superior to the typical speeds of bodies belonging to the solar system, which indicates that its kinetic energy is considerably large. This energy acts as a kind of natural stabilizer that makes it difficult for minor external forces such as variations in solar wind pressure to produce detectable deviations. For this reason, researchers anticipated that the probability of finding significant alterations was low. Even so, they preferred to rely on concrete data rather than assumptions, since each real observation provides essential information about how these visitors interact with the extreme conditions generated by the Sun. Another important aspect for understanding this interaction is the physical composition of the object. Although the internal structure of 3I Atlas is not yet known exactly, the measurements collected by different telescopes have allowed the inference that it is a body capable of maintaining its integrity, even in the face of an energetically dynamic environment. This is observed in the way its brightness increases gradually as it approaches the Sun, without presenting abrupt changes or irregular patterns that would normally indicate unstable activity. When an object has a surface composed of highly volatile or extremely fragile material, it can react more drastically to solar heating or to the impact of energetic particles. In contrast, 3I Atlas showed moderate and consistent material release, suggesting a relatively resistant surface capable of absorbing part of the energetic impact without significant alterations in its dynamics. The study of these interactions is not new, but each interstellar object offers a unique scenario due to its external origin and the different conditions under which it formed. Objects that developed in other stellar systems may contain compounds that respond differently to solar radiation. That is why 3I Atlas represents an exceptional opportunity to compare how materials formed in other galactic regions react to the activity of our star. During the period of solar intensification, several instruments detected very slight changes in the distribution of the coma, which coincided with the natural increase in temperature as it approached the Sun. However, these changes did not alter its nucleus or its displacement. In other words, the interaction existed, but it did not have the strength or magnitude sufficient to cause a measurable deviation. In the scientific field, understanding this type of resistance is indispensable because it allows improvement of the models that predict the behavior of bodies in transit. Orbital calculations do not depend solely on gravity. They must also consider non-gravitational forces such as reaction to gas release, solar heating, and solar wind pressure. In the case of 3I Atlas, the models used before the solar explosions already incorporated these variables. That is why, when the explosions began, astronomers were able to compare in real time the precision of their predictions with what was actually happening. The coincidence between the calculated data and the observed data strengthened the conclusion that solar influence, although present, was not sufficient to modify the object's trajectory. Another relevant issue is time. Interactions between energetic particles and small bodies also depend on how long they remain exposed to the solar wind flow. 3I Atlas travels so fast that any external influence has a limited period of effect. This rapid movement further reduces the possibility that alterations generated by the Sun accumulate enough to produce a deviation. In that sense, the combination of considerable mass, high speed, and stable dynamic behavior creates a scenario in which solar activity becomes a secondary observational factor, useful for observation but dynamically irrelevant to its trajectory. All this technical understanding allowed the teams to continue collecting data with confidence, knowing that the most important thing was to measure precisely and compare each record with the established baseline. The instruments continued to observe the object from different wavelength ranges, allowing verification that neither the shape of the coma nor the general brightness of the object presented unexpected patterns. The consistency of these measurements was essential to rule out any significant orbital effect. In this way, the period of solar activity not only served to demonstrate the resilience of 3I Atlas, but also to improve understanding of how interstellar objects interact with our stellar environment under extreme conditions. As the analysis progressed, the scientific community began to understand more clearly that the solar explosions, although extraordinary, had not produced dynamic alterations on the object. This conclusion, however, did not mean that monitoring could relax. On the contrary, the next stage would be crucial to confirm whether the trajectory would remain stable once the solar environment returned to a less turbulent state. But up to that point, the evidence gathered reinforced an important result. Intense solar activity had not had the capacity to modify the course of the interstellar visitor. Before the most intense solar explosions began, the observatories had already gathered a solid set of data that would serve as a fundamental reference for evaluating any possible alteration in the trajectory of 3I Atlas. This prior phase is one of the most important within any orbital analysis, because without a detailed comparative base it is impossible to identify subtle variations. During the weeks prior to solar activity, the object was observed from various latitudes and with different instruments, which allowed precise positions to be obtained within the night sky. Each added observation contributed to narrowing the error margins and calibrating the models that would continue to be used when solar activity reached extreme levels. The interesting thing about this stage is that although it was an interstellar visitor, the quality of the data obtained allowed a trajectory to be constructed with a level of precision comparable to that of some bodies in the solar system itself. Ground-based telescopes dedicated to this type of tracking took advantage of nights with better atmospheric stability to record detailed coordinates of the object. In parallel, more advanced observatories such as the Vera Rubin Observatory were beginning to record deep images in which 3I Atlas appeared with sufficient clarity to allow extremely accurate measurements. Even deep space instruments such as the James Webb collaborated by providing complementary information in wavelengths that cannot be detected from the Earth's surface. This combination of optical, infrared, and spectral data allowed a clear panorama to be built about how the object behaved before the Sun increased its activity. Each measurement recorded during this stage served as a point within an orbital map that grew day by day. Astronomers constantly adjusted predictions by comparing observed data with mathematical models describing its movement. As more observations were incorporated, the orbital curve became more stable and the values obtained began to show notable coherence. It was precisely this coherence that allowed scientists to state with confidence that any subsequent variation would not be ignored or interpreted as error, but evaluated with extreme rigor. For that reason, the prior phase became the backbone of the entire analysis. In this initial period, moreover, the brightness behavior of 3I Atlas was recorded when it was still far enough from the Sun not to experience drastic changes due to thermal effects. Brightness measurements are important because they allow identification of possible signs of surface activity. Although the object showed a gradual increase in its luminosity, this behavior fully matched what was expected for an icy body approaching solar heat, without signs of irregularities that could suggest unstable activity or fragmentation. This initial brightness stability is a key indicator that the object's nucleus was not reacting abruptly, something that would later help distinguish between changes caused by the solar environment and changes caused simply by natural heating. During this prior stage, scientists also analyzed the distribution and shape of the coma, which was already perceptible though still moderate. Its shape was consistent with an object that releases particles in a relatively uniform way, without marked eccentricities. This reinforced the idea that the surface structure of 3I Atlas was solid enough not to experience unpredictable detachments. The stability observed in the coma before the solar events would be a vital reference later when subsequent data needed direct comparisons. In this sense, every recorded detail was an indispensable piece for the final evaluation. Another important component of this phase was the measurement of the object's radial velocity. The observatories collected multiple spectra that allowed determination with high precision whether its velocity showed minimal variations. The consistency of these values confirmed that the object was not experiencing unexpected accelerations or decelerations. In bodies such as active comets, gas release can generate small forces that slightly alter velocity, something that models must consider. However, up to that point, 3I Atlas showed extremely regular behavior, which facilitated the construction of highly reliable orbital prediction models. It is also relevant to highlight that the observatories adjusted the data taking into account non-gravitational forces derived from solar heating. These adjustments are common when studying comets because material release can generate thrust. However, the values calculated for 3I Atlas indicated that these effects were reduced and remained within expected limits. This eliminated the possibility that the object presented unstable behavior before the period of solar explosions, which was essential to confirm that any future variation should be investigated with special attention. The prior phase also allowed verification of the stability of the orbital direction. The calculations showed that the approach angle to the Sun remained practically identical in all simulations and predictions made. These data were so consistent that they offered a high degree of certainty that the object's trajectory was well defined even before entering zones where solar activity could minimally influence. When 3I Atlas began to receive more radiation, this reference line allowed immediate comparison of any detected variation, ruling out the possibility that observed changes were simply adjustments inherent to the calculations. As more observations were gathered, the predicted trajectory became so precise that even the smallest variations could be detected clearly. This level of detail reflects the efficiency of modern instruments capable of observing extremely distant objects with impressive accuracy. That is why, when the solar explosions reached their maximum intensity, scientists knew they had in their hands the ideal base for evaluating any real effect on the object. If the solar wind had produced any minimal alteration, it would be visible when compared to these initial data. However, this prior phase already showed a pattern of stability that would later be confirmed even under extreme solar conditions. With all these data gathered, the scientific community was prepared to analyze each subsequent change with a solid criterion. The importance of this phase lies not only in the precision of the measurements, but in the clarity with which they demonstrated that 3I Atlas maintained a stable trajectory before facing an energetically intense solar environment. This initial stability would become one of the pillars of the later conclusions, as it offered the certainty that any alteration, however minimal, would not go unnoticed. When the Sun reached the highest point of its recent activity, the observatories were already prepared to record every relevant change, both on the solar surface and in the behavior of 3I Atlas. This phase was one of the most anticipated because it represented the exact moment when the interaction between solar radiation, the solar wind, and an interstellar object could be evaluated in real time. The flares began to rise with an intensity that exceeded the values observed days before, and the instruments installed on specialized satellites confirmed that the released energy was large enough to temporarily affect the density of the solar wind in various regions of the inner solar system. This increase in solar activity generated shock waves that traveled at high speed and that could modify the pressure exerted on small bodies in transit. While this was happening, the telescopes monitoring 3I Atlas adjusted their observation frequency. During this period, measurements became more frequent with the aim of having as continuous a sequence as possible of its apparent position in the sky. The priority was to detect any deviation, however minimal, by comparing each record with the reference data accumulated before the solar event. As the first highly energetic particles began to propagate from the Sun, the teams knew that this was the critical observation window. If the solar wind had any influence on the interstellar visitor, it would be during this period that the first signs would appear. The first records during the most intense phase of solar activity showed that the brightness of 3I Atlas increased slightly, a behavior that could be associated with the natural increase in temperature due to proximity to the Sun. This increase recorded in different instruments matched the patterns already observed previously, indicating that it was not an unusual effect generated exclusively by the solar explosion. Even so, scientists carefully compared the values with previous data to confirm that there was no abrupt variation that could suggest a direct impact from the energetic particles. Up to that point, the brightness behavior continued to be consistent with expectations without showing signs that required reinterpretation. As the solar wind intensified, the spectrographs on board several satellites recorded changes in the density of the plasma moving toward different regions of space. These data were synchronized with optical observations to determine whether there was any correlation between the arrival of these particles and the positioning of 3I Atlas. The idea was to check whether variations in solar wind pressure could generate a thrust that minimally altered its apparent trajectory. However, the initial calculations already showed that the object's mass and high velocity made it very difficult for this pressure to generate a significant effect. As observations progressed, all the collected data reinforced that conclusion. Images captured by instruments operating in ultraviolet wavelengths were also analyzed, because these bands allow better observation of changes in the surface material distribution of active objects. These records were important for detecting sudden alterations that could influence the way the object releases material as it approaches the Sun, but during the strongest peaks of solar activity no irregular changes were observed in the visible surface of the object. The coma distribution remained relatively uniform, without unexpected variations in its structure. This reinforced the interpretation that the interaction between the object and solar activity, although present, was not generating a dynamic effect that could alter its movement. A particularly interesting aspect during this stage was the temporal comparison between the arrival of coronal mass ejections and the sequence of positions recorded by ground-based telescopes. The ejections that reached space near the ecliptic took a certain time to travel the distance from the Sun to the regions where 3I Atlas was located. This transit time allowed prediction with relative precision of when the energetic particles would influence its environment. The researchers carefully compared these moments with the observed positions of the object, looking for any deviation that could coincide with the arrival of a shock wave or a significant variation in the solar wind. The results showed that there was no correlation between these arrivals and possible variations in the trajectory. Throughout this entire phase, the importance of coordination between different observatories was fundamental. While specialized satellites analyzed solar activity from Earth orbit, ground-based and space-based telescopes dedicated to deep sky observation focused on obtaining the most precise positions possible of the interstellar visitor. Thanks to this cooperation, the acquired data allowed the construction of an uninterrupted sequence showing how the object continued its displacement without deviations. Each new observation reaffirmed that solar activity, despite its intensity, was not modifying the predicted course. Continuous tracking also allowed evaluation of whether the energy released by the Sun could have accelerated the release of gases or particles on the object's surface, which in theory could generate an additional force affecting its trajectory. However, the data obtained during the period of maximum solar activity showed stable behavior, without indications that the object had experienced unusual surface activity. The coma maintained a uniform appearance and the spectra did not show significant changes in the apparent composition of the released material. This indicated that even in an environment of elevated radiation, the physical response of 3I Atlas aligned with previously observed patterns. As the days progressed within this critical period, the teams managed to gather a set of data complete enough to begin outlining preliminary conclusions. The absence of perceptible deviations, both in position and in the object's surface behavior, reinforced the interpretation that the trajectory remained stable, even under extreme solar conditions. There were no signs suggesting a notable dynamic impact. This result matched the previous models that anticipated minimal influence from the solar wind on an object with these characteristics. What made this phase particularly valuable is that it provided direct evidence obtained during one of the most active solar episodes of the cycle. This allowed confirmation with certainty that even under intense conditions, the orbital dynamics of 3I Atlas remained practically unchanged. This observation not only strengthened understanding of the object's behavior, but also offered essential information for studying how interstellar visitors interact with the solar environment during moments of elevated activity. When solar activity finally began to decrease, the observatories entered one of the most important phases of the process, comparing the data obtained during the period of maximum intensity with subsequent records, analyzing every detail with the highest precision available. This stage was crucial because it allowed evaluation not only of whether the trajectory of 3I Atlas had suffered any alteration during the solar explosions, but also whether there were delayed effects that could manifest afterward. In many solar phenomena, especially coronal mass ejections, particles continue to flow through space even hours or days after the initial event. That is why scientists wanted to ensure that no late variation was affecting the object's dynamics. The first observations made right after the decrease in solar intensity showed that the position of 3I Atlas coincided almost exactly with the predictions made before the event. This result was especially significant because it confirmed that the trajectory showed no apparent changes and followed its course as expected. The instruments projected its position based on highly refined orbital calculations, and when overlaying the new data on the previous model, the coincidences were so clear that they reinforced the conclusion that solar activity had not had a detectable dynamic impact. The analysis continued with the measurement of brightness, an important indicator for evaluating whether the object had experienced any surface change beyond natural thermal effects. If the solar wind particles had significantly affected the surface of 3I Atlas, an irregular increase or decrease in its luminosity might have been observed. However, subsequent records showed a stable trend, consistent with progressive heating as it approached the Sun. There were no unexpected peaks or abrupt drops that could suggest an unusual event caused by the solar explosions. This stability was key to ruling out the possibility that the object had experienced any fragmentation process or accelerated material release during the period of intense activity. The spectra obtained in this subsequent stage also provided valuable information. When analyzing the apparent composition of the gases emitted by the object, researchers noted that there were no relevant changes that could be associated with intense interaction with highly energetic particles. The spectral distribution followed a pattern completely compatible with the expected behavior of an interstellar object approaching the Sun. This meant that even under conditions of elevated radiation, the object's surface had not reacted unusually, which reinforced the idea that its internal structure was sufficiently stable and resistant. In addition to brightness and composition analyses, photometric and astrometric comparisons were made with images obtained before and after the solar explosions. These comparisons allowed verification with exactness whether the apparent position of the object showed any minimal deviation that had not been detected in individual measurements. Using advanced image stacking techniques and differential analysis, the teams determined that the variations were so small that they fell completely within the natural margin of error of the instrumentation. This implied that from a physical point of view there was no evidence that the solar wind had generated a force large enough to deviate the trajectory of the interstellar visitor. Another important factor considered in this stage was the evaluation of solar radiation pressure. Although this pressure varies with the intensity of solar activity, the models showed that even during the highest peaks of the explosions, the force exerted on an object of the estimated mass of 3I Atlas was insufficient to generate a measurable deviation. Subsequent calculations confirmed this conclusion, demonstrating that the additional pressure during the flares did not significantly alter the object's movement. This coherence between theoretical models and observed data provided solid support for stating that the object's orbital stability had not been compromised by the temporary increase in solar radiation. One aspect that particularly caught the attention of researchers during this stage was the way the coma maintained its relatively uniform structure. If the energetic particles had significantly impacted the object, temporary deformations or changes in the direction of the ejected material might have been observed. However, the images taken after the period of maximum activity showed that the coma followed a pattern similar to that observed weeks before. This indicated that the surface material release continued to be moderate and consistent, which was one more indicator of the object's physical stability. As the accumulated data was analyzed, the conclusion became increasingly clear. 3I Atlas had passed through a period of intense solar activity without showing signs of orbital deviation. This not only confirmed that the solar wind had very limited influence on the object, but also highlighted the importance of the models used to predict its behavior. The coincidence between predictions and subsequent observations reinforced confidence in the orbital analysis, demonstrating that the trajectory of the interstellar visitor was well defined even before the solar phenomenon. The possibility of secondary non-gravitational effects such as slight acceleration caused by material release was also considered. This type of effect is usually observed in active comets, but in the case of 3I Atlas, the values recorded after the period of solar activity showed such a small acceleration that it did not contribute to any significant alteration in the trajectory. This confirmed that although the object showed moderate activity as it approached the Sun, that activity was not strong enough to generate forces competing with its hyperbolic trajectory. For the scientific teams, this subsequent stage had particular value because it provided the definitive confirmation that 3I Atlas maintained stable movement, even in the face of one of the most intense solar phenomena observed in that period. Every observatory involved shared the same results. No orbital changes were observed, there were no unexpected alterations in the coma, no irregular variations in brightness were detected, and no modifications in radial velocity were recorded that could suggest a dynamic response to the increase in solar wind. As the analyses concluded, the scientific community understood that this stability was not a coincidence, but a reflection of the object's physical properties. Its mass, velocity, composition, and internal structure worked together to keep its trajectory firm, even in an environment where solar conditions were extraordinarily intense. In this way, the subsequent phase confirmed what the preliminary data already indicated. 3I Atlas had notable dynamic resistance and its trajectory had not been affected by the solar explosions. When the scientific teams confirmed that the trajectory of 3I Atlas had shown no detectable deviation after the period of solar explosions, an equally important stage began. Understanding why the object had remained so stable, even in the face of one of the most intense solar phenomena of the cycle? This question did not arise from doubt, but because every detail about the object's dynamic resistance offered key information about its internal structure, composition, and physical behavior. Although the data already clearly showed that the solar wind had not been able to alter its course, the researchers wanted to thoroughly understand the physical reasons behind that stability, since this knowledge could be applied to future studies of interstellar objects. The first reason highlighted was the extremely high speed at which 3I Atlas travels. An interstellar object entering the solar system brings with it a quantity of kinetic energy far superior to that of bodies that regularly orbit the Sun. This speed not only makes its transit rapid, but also acts as a kind of dynamic anchor that keeps its movement firm even against external influences. To alter the trajectory of an object moving with so much energy, an external force would need to exert substantial and sustained pressure, something that the solar wind cannot provide, even in its most intense phases. The second reason lies in the estimated mass of the object. Although the exact size or internal density of 3I Atlas is not yet known, calculations based on its brightness, coma, and the way it interacts with sunlight suggest that it is a body with sufficient mass to resist minor dynamic changes. Solar wind pressure, although real, is extremely small compared to the inertia of an object with these characteristics. This is why most solar system comets also do not experience significant deviations during solar explosions, unless they have extremely fragile nuclei or uncontrolled surface activity, something the data do not suggest in the case of the interstellar visitor. The third reason is related to the object's composition. Although the instruments have not yet identified a complete spectral signature revealing all the chemical components present, scientists have observed that its surface activity is moderate and stable. This indicates that the object probably possesses a mixture of materials that react predictably to solar heating, without abrupt releases of gas or dust that could generate irregular accelerations. When a cometary nucleus is highly volatile or unstable, it can produce jets or emissions of material that slightly alter its velocity and trajectory. But 3I Atlas showed no signs of irregular activity, suggesting that its internal structure is solid enough to maintain consistent behavior. Another key reason has to do with the uniform distribution of the coma recorded by the observatories. If the object had experienced a sudden increase in material release due to interaction with energetic particles, the coma would have shown deformations or abrupt changes in its density. However, the data showed a stable structure, indicating that the object released material in a regular and controlled manner. This stability allowed ruling out the possibility that surface activity had contributed to any dynamic change during or after the solar explosions. Radiation pressure was also evaluated in detail. Although sunlight exerts a constant force on all bodies in the solar system, this force is extremely weak when compared to the inertia of an interstellar object on a hyperbolic trajectory. The pressure could minimally influence very small particles, but not a body with considerable mass. Even during solar explosions, when light intensity temporarily increases, the change in pressure is insufficient to cause detectable deviations. The calculations performed by the models showed that any acceleration generated by radiation would be thousands of times smaller than necessary to alter the object's orbit. Non-gravitational forces were also carefully analyzed. These forces, generally caused by gas release from the nucleus, can slightly modify the trajectory of active comets, but in the case of 3I Atlas, the recorded values were so small that they fell within the limits expected for a body with moderate activity. This means that even if small accelerations produced by sublimation of surface material existed, these forces did not have the magnitude sufficient to significantly alter its trajectory. The interaction between the solar wind and interstellar objects is a relatively new field of study. Therefore, each observation of 3I Atlas offered valuable information about how these visitors respond to extreme solar phenomena. The data collected during the solar explosions represented one of the most complete records obtained so far about an interstellar object facing high-energy conditions. The object's stability, even during the activity peak, suggested that its internal structure is more resistant than some models might have anticipated. Another reason why no deviations were observed has to do with the very nature of its hyperbolic trajectory. This type of trajectory implies that the object is not gravitationally bound to the Sun. Instead of orbiting around it, it simply passes through the solar system following an open line. Objects with hyperbolic trajectories require extremely large forces to modify their course, much greater than those the solar wind can generate. This is one of the reasons why interstellar visitors tend to maintain a stable trajectory, even when facing varied solar conditions. Finally, the efficiency of modern instruments allowed confirmation of the object's stability with notable precision. The telescopes used during the observation had advanced tracking systems that allowed recording extremely exact positions, making it possible to detect minimal deviations if they existed. But the data showed no appreciable changes, which further reinforced the conclusion that the object had passed through the entire period of intense solar activity without showing dynamic alterations. The sum of all these factors demonstrates that the stability of 3I Atlas in the face of solar explosions was not a fortuitous event, but the result of its speed, mass, composition, internal structure, and trajectory. All this contributed to the interstellar visitor maintaining its course even at a time when the Sun was releasing large amounts of energy into space. While the tracking of 3I Atlas progressed and the data confirmed notable stability in its trajectory, scientific attention turned to another fundamental aspect: the role played by the different observatories responsible for analyzing both the object's behavior and the solar environment conditions. Each instrument with its specific capabilities contributed an essential piece to the puzzle, allowing the construction of a complete and highly reliable panorama of what was happening. The combination of ground-based and space-based observations was crucial, as it offered a reach that no individual system could have achieved on its own. This stage of the analysis focused not only on the object, but also on understanding how each technological team contributed to validating that the trajectory remained intact. One of the most important instruments throughout the process was the Vera Rubin Observatory, whose design allows recording large areas of the sky with exceptional depth. Although it was still in an initial operational phase, it managed to provide high-resolution images that captured the object's displacement with extraordinary precision. The telescope's ability to perform deep and continuous surveys ensured that the recorded positions were detailed enough to identify even the most subtle deviations. Its measurements, repeated constantly during the period before, during, and after solar activity, served as a solid reference for verifying the orbital stability of the interstellar visitor. Another key instrument was the James Webb Space Telescope, whose sensitivity in the infrared allowed observation of object characteristics that were not detectable from the Earth's surface. Although Webb did not dedicate exclusive observations solely to 3I Atlas, its complementary records allowed measurement of thermal activity and surface material emission in wavelengths that offered clues about how the object responded to the Sun's heat. Webb's ability to observe without atmospheric interference provided crucial data on emission stability, reinforcing the idea that the object did not experience abrupt changes related to intense solar activity. The role of the Solar and Heliospheric Observatory, a satellite designed specifically to monitor solar activity, was equally indispensable, although it did not observe 3I Atlas directly. Its task was to measure with precision the solar explosions, coronal mass ejections, and variations in solar wind intensity. Thanks to its continuous vigilance, scientists were able to synchronize each solar event with the object's observations, determining whether the arrival of a particle wave coincided with measurable changes in its trajectory. The Solar and Heliospheric Observatory acted as the solar clock of the entire analysis. Each explosion, each increase in radiation, and each solar wind fluctuation was recorded exactly, allowing teams to compare these data with the observed positions of 3I Atlas. In addition to the Solar and Heliospheric Observatory, measurements from the Parker Solar Probe offered complementary data from the inner regions of the heliosphere. Its unique ability to approach the Sun more closely than any other mission allowed direct recording of the speed, density, and behavior of the solar wind from areas extremely close to the solar surface. These data were fundamental for modeling how energetic particles spread through space and for estimating what level of pressure they could exert on small bodies in transit. Although Parker did not directly observe the interstellar object, it provided essential information about the surrounding environment, helping to understand clearly whether there was a possibility that solar activity would influence its movement. Traditional ground-based telescopes also played an important role during this period. Observatories located in different regions of the planet, from North America to Europe and South America, contributed constant measurements that allowed tracking the object's displacement throughout the night, taking advantage of time differences between continents. This global coordination allowed positions to be recorded without prolonged interruptions, significantly increasing the precision of orbital models. For astronomers, every observation counted. Even seconds of data could make a difference when trying to detect extremely small deviations. The coordination between these observatories did not happen by chance. It was the product of meticulous scientific planning. When it was confirmed that the Sun was entering a period of intense activity, protocols were activated to increase the observation frequency of the object. Scientific centers exchanged their data in real time, adjusting strategies according to the needs of each day. This cooperation not only reinforced the precision of the records, but also allowed validation of results through multiple independent sources. When different instruments located in different places and operating under different wavelengths agreed that there were no orbital deviations, the conclusion became practically irrefutable. The analysis also benefited from the use of advanced computational models that integrated data from all these observatories. These models simulated how the object should behave if its trajectory remained stable and compared the results with real observations. In each simulation, the coincidence between real data and projections demonstrated notable congruence. This meant that the models were not only working correctly, but that the object's trajectory was coherent even under the pressure of a temporarily more aggressive solar environment. Thanks to these models, scientists were able to rule out hypotheses suggesting delayed effects from solar activity, even if the arrival of energetic particles had produced a small disturbance. The models detected that this disturbance would have amplified over time, causing the trajectory to deviate slightly in subsequent days. However, nothing like this happened. The recorded positions maintained a uniformity that made the object's dynamic resistance and the absence of any lasting effect derived from the solar explosions clear. The joint role of all these observatories demonstrated that scientific precision in astronomy depends not on a single instrument, but on the sum of multiple complementary perspectives. Each one contributed an essential part of the analysis. Some observed the sun, others observed the object, some measured its composition, others measured its brightness or coma, and each piece fit perfectly into the final whole. This coordination allowed reaching a robust conclusion. The trajectory of 3I Atlas remained stable before, during, and after the period of greatest solar activity. With the confirmation obtained by all the observatories, the moment arrived to present the most updated orbital state of 3I Atlas, based exclusively on data measured after the period of solar explosions. This analysis formed one of the most relevant stages of the tracking because it allowed verification of whether the trajectory projected in the initial models continued to be valid or whether it needed to be modified with new parameters. Each position recorded after the episodes of solar activity became a key point for consolidating the orbital curve. As the data was introduced into the mathematical models, a consistent result emerged. 3I Atlas maintained exactly the course calculated before the sun's flares. Astronomers first reviewed the positions obtained in ground-based observations that were compared with predictions made days before. The coincidence was so clear that the teams confirmed that the deviations found were completely within the natural margin of error of the instruments. This meant that the object continued its displacement exactly as expected, without showing signs of small accelerations or alterations caused by the solar environment. Additional tracking measurements also showed that radial velocity remained stable, adjusting precisely to the predicted values, something that is only possible when an object preserves its orbital dynamics without significant external interference. Spectral data obtained by space instruments verified that surface material release followed a stable and consistent pattern. The gradual increase in thermal activity continued to respond to the object's natural approach to the sun, without showing anomalous variations. This information was also useful for confirming that the object did not present internal changes or fractures that could modify its movement. In comets with unstable nuclei, sudden releases can slightly alter the trajectory, but in this case spectral stability reinforced the idea that 3I Atlas maintained a solid internal structure without exhibiting unexpected events. With these data, the mathematical models were refined. The hyperbolic trajectory was recalculated using high-precision astrometric methods, incorporating the most recent positions. And once again, the results showed that the interstellar visitor followed a stable course. The calculated eccentricity remained practically unchanged, which is one of the strongest indicators that the sun's gravitational force had not changed its behavior or exerted any unexpected influence on the object. The analysis also confirmed that the orbital inclination remained within expected values, reinforcing that no external force had altered its orientation in space. Another essential aspect reviewed in this stage was the escape velocity associated with its trajectory. Since 3I Atlas follows a hyperbolic path, its velocity exceeds the velocity that the sun can retain under its gravity. This characteristic is one of the fundamental reasons why its trajectory is so stable. Even under intense solar conditions, the object's kinetic energy is large enough not to be affected by small variations in solar wind pressure or radiation. The updated calculations demonstrated that its velocity remained within the projected range, further reinforcing confirmation of its stable course. The observatories also evaluated whether there were phase differences between the orbital models calculated by different institutions. When several independent teams reach similar conclusions, the reliability of the analysis increases significantly. In this case, models developed by institutions from different countries agreed that there was no measurable alteration in the orbit. After the period of solar explosions, the observed positions and future predictions continued to align, consolidating the certainty that the object maintained its original trajectory without detectable interference. As the analysis progressed, an even clearer panorama emerged. Not only had the trajectory remained stable, but the most sensitive orbital values, such as the distance of approach to the Sun and the projected minimum distance with respect to Earth, continued to match previous predictions. This point was of special interest because any slight variation would have modified the minimum distance values. However, the data demonstrated that there was no reason to significantly recalculate these values. This reinforced the idea that the interstellar visitor would pass through the inner region of the solar system following exactly the planned path, without showing any unusual response to the intense solar conditions it faced. The consistency of all this information also allowed scientists to confirm that the interaction between solar radiation and the object continued to be as expected for a body of this nature. The absence of significant alterations in its trajectory suggested that radiation pressure was not acting differently than anticipated. This result provided important data not only for the study of 3I Atlas, but also for future interstellar visitors, because it served as a reference for understanding how the solar wind and radiation affect these objects when crossing regions of high solar activity. Once the orbit stability was verified, the teams adjusted the models to project the object's future positions. These models included a detailed prediction of its displacement during the coming weeks. When compared with the most recent observations, it was verified that there were no deviations suggesting a need to modify the orbital map. This behavior reaffirmed that the hyperbolic trajectory would follow its planned course without showing unexpected curves or accelerations that altered its passage through the solar system. In addition to orbital stability, the analysis also evaluated the object's rotation, although the available observations do not allow determination with absolute precision of the rotation period. Some periodic changes in luminosity suggested stable rotation. This behavior, although not directly related to the trajectory, was important for confirming that the object did not experience abrupt internal changes that could influence its displacement. Stability in rotation reinforced the idea that the interstellar visitor's structure remained solid and balanced. Astronomers also examined the direction of the material forming the coma. When an object experiences strong interactions with the solar wind, this material tends to exhibit significant curvatures or distortions. However, subsequent images showed a coma whose behavior remained coherent with what was observed before the period of solar explosions. This demonstrated that particle pressure had not generated important deformations, further reinforcing the conclusion that solar interaction had not been sufficient to dynamically alter the object. As the models were updated and observations continued to confirm the stability of its movement, the scientific community reached the definitive conclusion. The trajectory of 3I Atlas remained completely intact. The intense solar episodes had not produced alterations in its orbit, and there was no observable evidence of dynamic effects derived from the solar wind. This stability not only confirmed the physical resistance of the object, but also the robustness of the orbital prediction models used from the beginning of its tracking. With the trajectory of 3I Atlas confirmed as stable even after the period of the most intense solar explosions, scientific attention naturally turned toward the following weeks, a crucial phase for understanding how the object would evolve as it continued its passage through the inner region of the solar system. Although the data collected up to that point showed extremely consistent behavior, astronomers knew that monitoring could not relax. Each passing day represented a new opportunity to obtain unique information about an interstellar visitor that would not return to cross our environment. In this sense, the following weeks would not only be a period of vigilance, but a strategic stage to deepen general knowledge of these bodies. The first aspect scientists considered was the thermal evolution of the object as 3I Atlas continued approaching its point of maximum solar exposure. The instruments expected to record a gradual increase in its surface activity. This type of variation is completely normal and is due to natural heating caused by solar radiation. However, although it was an expected process, it was important to measure it precisely. Higher temperatures could cause a moderate increase in material release, altering the appearance of the coma or causing variations in brightness. This would not mean orbital instability, but it would offer valuable clues about the nucleus composition and about how interstellar materials react to solar heat. The next weeks would also be essential for monitoring possible spectral changes. Telescopes equipped with high-sensitivity spectrographs would continue measuring the reflected and emitted light from the object to identify how its visible composition evolved. Although the data obtained so far showed notable stability in gas release, the approach to the Sun could make visible substances that remained frozen in earlier stages. Spectral variations could reveal new chemical signatures, providing additional data about the environment in which the object formed long before entering the solar system. This information is especially valuable because interstellar objects carry material that originated in regions where physico-chemical conditions may differ from those prevailing in our own stellar system. Another important tracking point would be the evolution of the coma. Although its distribution had been stable and uniform until now, astronomers expected to observe subtle changes as the object received more heat. These changes would not be related to the intense solar activity already past, but to the natural behavior of an icy body approaching the Sun. The shape, density, and expansion of the coma could help infer whether the nucleus presents zones with different activity levels or whether there is variation in the materials present on its surface. Although the coma does not directly influence the object's trajectory, its study is fundamental for understanding the physical structure of the nucleus and for comparing its behavior with that of other previously observed interstellar visitors. Furthermore, the next weeks would serve to consolidate the orbital models that would continue to be used even when the object began to move away from the Sun. During this phase, each recorded position would help refine the parameters of its hyperbolic trajectory, allowing even more precise predictions about its future velocity, exit angle, and the way it would leave the solar system. Knowing exactly how its passage through the inner region evolves will allow better understanding of the Sun's gravitational influence on objects from other stellar systems, contributing to improving the models that describe the dynamics of these open trajectories. In this period, comparative models with other interstellar objects were also expected to gain importance. Although 3I Atlas did not show unexpected behaviors during solar activity, astronomers wanted to compare its characteristics with those recorded in other visitors such as Oumuamua or Borisov. This type of comparison would allow understanding which properties are common among interstellar objects and which are particular to each one. Observations in the coming weeks would be vital for this comparison, especially if 3I Atlas continued to show predictable and stable behavior that facilitated analysis as the object continued to slowly move away from the environment of maximum solar radiation. It was also expected that the solar wind would return to more moderate levels, which would simplify observations. However, scientists would not lower their guard, since there still existed the possibility of new solar explosions or variations in the solar magnetic field. Although previous data had demonstrated that these conditions did not affect the trajectory of the interstellar visitor, monitoring each event would allow continued validation of the models describing the interaction between the solar wind and bodies in transit. Another area of interest for the coming weeks was the tracking of the object's rotation. Although its rotation period was not known exactly, periodic changes in luminosity suggested that its rotation was relatively stable. Continuous observations could help refine this value, allowing determination with greater accuracy whether the object presented subtle variations related to solar heating or surface material loss. This information would offer additional clues about the nucleus structure and internal mass distribution. Astronomers also focused part of their attention on the projected distance of the object with respect to Earth. Although it was already confirmed that its trajectory represented no risk and that its passage would be distant, minimum distance calculations are always reviewed precisely to confirm that the models continue to align with observations. The weeks following the period of solar activity would be ideal for accurately measuring this minimum distance. Although there was no concern from a dynamic point of view, precise measurement of this approach would allow further validation of the orbital models used. With all this scientific expectation, the following weeks represented a unique opportunity to obtain the last details about the behavior of the interstellar visitor before it continued its path outside the solar system. As it moved toward more distant regions, observations would naturally become more difficult due to the gradual loss of brightness. That is why astronomers would intensely take advantage of this period to perform exhaustive measurements, obtain additional images, record more complete spectra, and consolidate the final models. Every observation would count because once 3I Atlas definitively undertook its exit toward interstellar space, the opportunity to study it in such detail would not present itself again. In the end, the coming weeks would not only serve to confirm the already observed stability, but also to close one of the most complete studies on an interstellar visitor in recent times. The data would continue to accumulate and the final conclusions would be the combined result of thousands of coordinated observations by different telescopes, laboratories and scientific teams around the world.